say and you take the order of vanishing at certain points, and you take the leading coefficient of Taylor series. So the zeta function sides of those two theorems are very defined purely analytically, whereas the algebraic K-series side are defined purely algebraically, I guess, except for this regular part. This regular part is also, this regular part is, I don't know, it's also sort of defined algebraically. So those two theorems can be generalized, has a vast generalization to the following. The first is the Quillen-Borel theorem, which says algebraic K groups of a number of integer of number field are all finitely generated. So you may ask, what about the ranks? So in even dimensions, it's actually going to be just finite. So the finite abelian group. In all degrees, you can say the dimension of rational algebraic K group of OF is equal to those numbers which are precisely the orders of vanishing of zeta F at the negative integers. So in this sense, this Quillen-Borel theorem generalizes the Dirichlet-Ullian theorem, at least the rank part. And how about the class number formula? The class number formula now is generalized to zeta F star, again, the leading coefficient in Taylor series, is equal to plus minus the ratio of successive algebraic K groups of OF. And in the numerator, I don't need to take torsion subgroups because this group is known to be a finite abelian group. And in the denominator, I have to take a torsion sub because it might be infinite. And this formula holds up to powers of 2. And there's also, we need to add this Borel regulator, which is a generalization of the Dirichlet regulator in the class number formula. And also this plus minus sign can be determined using the functional equation. Because this number, after all, is related to the value of zeta F at a positive integer n. And if for those positive values, of course, it's going to be a positive number. So you can use functional equation to determine what this plus or minus signs are. So those two theorems are vast generalizations of the Dirichlet-Ullian theorem and the class number formula, respectively. And it hints very deep connections between number theory, between this L functions, and the theory of algebraic K theory, or more generally homotopy theory. Because you can see this side again, the zeta side is defined purely analytically, whereas the algebraic K theory side, this is defined purely algebraically. So let me explain to you, give you some rough sketch of how on earth can we connect zeta functions to algebraic K groups. Here's the diagram. Fix the prime P. We want to connect something called p-adic L function, which is sort of a p-adic version of L function, to certain algebraic K groups. And here I have to do some modification. Like I need to invert P in the range of integers number field, and I want to capture the p-adic information so I complete the algebraic K group. And how are those two objects related to each other? The first step is the Iwasawa theory in number theory. And Mazur and Wiles, they prove the Iwasawa main conjecture, which says, so if you consider the Itow cohomology of the range of integer of F, and then you invert P, and you add all P power roots of unity to it, then on this side, there will be a Galois action, or Frobenius action. And the Iwasawa main conjecture basically says the characteristic polynomial of, say, of the Frobenius action on the left-hand side is basically the same as the p-adic L function. This is a pretty striking fact that this side, we have something, the Galois action characteristic polynomial, which is a p-adic L function. That's something defined analytically. This was proved by, this Iwasawa main conjecture was proved by Mazur and Wiles. And then from here, once we know the Frobenius action, and then we can cook up, then we will be able to compute this continuous group cohomology of the algebra of the Itow cohomology group of OF, where this Z P cross should be thought of as the Galois group of sort of as a Galois group, because after all, the Galois group for adding all P powers of unity is precisely Z P cross. And from there, there's a Hochschild-Linden-Serre spectral sequence where we can basically the input are those group cohomologies of Itow cohomologies of number fields, and we can use it to kill or the p power roots of unity. And here, the reason we have to have this 1 over p here is otherwise adding p power roots of unity will not be an tau extension. So that's why I have to invert p in the setup. And it is then one in the early days of this, when it is Lichtenbaum who observed that the universal main conjecture implies the tau cohomology version of the Quillen-Lichtenbaum conjecture, which I will show on the next slides. So now we have related PIDL functions with the tau cohomology group of OF, and the UMS how is it related to algebraic K group. So the next step is a Thomason spectral sequence, which says the tau cohomology groups of OF is actually they form the E2 pages of a spectral sequence to compute K1 co-algebraic K group of OF. So here the K1 is the same P as this P. It's the same prime. It is the same prime. So of course you have K1 co-algebraic K group, which is pretty close to the actual algebraic K group. So of course there's a K1 localization map. So you may ask, how are those two things related to each other? Well, for algebraic K group itself, there's a similar spectral sequence called the motivic spectral sequence, which was formulated later than the Thomason spectral sequence. And from between motivic and a tau cohomology groups, there's a comparison map. And maybe before that I should mention, so far we have seen 3 spectral sequences in this diagram. And the one important fact is that in all those 3 for all those 3 spectral sequences, they collapse on the E2 pages when p is greater than 2. When p is equal to 2, they don't collapse on the E2 page. So that's why in the statement of the Quillen-Lichtenbaum in the previous page, everything is stated up to powers of 2. So that's why we have a powers of 2 here. It is because at odd primes, the spectral sequences collapse. So the comparison between algebraic K groups and its K1 localization reduces to the comparison between motivic and tau cohomology groups. And the final piece of the puzzle was proved by Blavatsky and in celebrated work of Blavatsky and Rost, which says the comparison map is an isomorphism in certain range. So that's how we can, yes?
Can I ask one question? When you talk about the tau cohomology of a number field, do you mean the spectrum of the ring of integers, or what kind of space or scheme you're talking about?
Yeah. I mean the spectrum of the ring of integers. I mean the spectrum of the ring of integers, maybe with p inverted.
Right.
Yeah, because we have to invert p in order to do this. Basically tau descent. We have to invert p to do this tau descent in the Hochschild-Linden-Serre spectral sequence step.
Okay, thank you.
And I guess this basically sort of connects the two sides, but let me show you about how do the numbers match. And here's how the numbers actually match. Assume f is strictly real for simplicity. But in that case, we don't need to deal with the regulator stuff. And again, assume p is odd, so that we just need to compare cohomology groups instead of algebraic K groups. So the first step is this is the tau cohomology version of the Quillen-Lichtenbaum that was observed by Lichtenbaum, and it follows from the universal main conjecture. So that's the first step, and this by this same p, I mean the two sides have the same p-adic valuations. So this follows from the universal main conjecture. And then by the Blavatsky-Ross comparison theorem, the two groups in this range, when n is greater than or equal to 1, the tau cohomology group of number fields agree with the motivic cohomology groups. And then from the motivic spectral sequence, the motivic spectral, because motivic spectral sequences collapse on those primes, so the sizes of the motivic cohomology groups agree with the sizes of the algebraic K groups. And finally, we have to get rid of this 1 over p, which is possible because the differences between those two algebraic K groups is given by the localization sequence in algebraic K theory. And you can check integrally the ratio between their sizes is coprime to p. So inverting p does not change the p-adic valuation of the size of algebraic K group. inverting p in the inside. So this is how on Earth we can manage to match the p-adic evaluation of the zeta function and the zeta function and 1 minus 2n with the sizes of algebraic K groups. And also let me show you a picture of the multiplic spectral sequence in Adams gradient. Again, when p is odd. So what are the input data? So the first piece of data is this is what we're asking row. So we have a 9 of slope 1, below which multiplic cohomology groups agree with Italco cohomology groups. And in the S equals 0, and that's the zeroth cohomology group 9, it actually vanishes unless t is positive. And in the 0, 0 set, that's when the t twist is n is 0, we got a single copy of ZP. And in the S equals 1, 9, that's the first cohomology 9, then this group, this is the units. This group is a unit, this is H1. Yeah, this is H1 of ZP of 1. And then in the S equals 2, 9, we get class group here and some other stuff. And finally, above the S equals 3, 9, it's all gonna be 0. And from there, we can just read off, and you can see the spectral sequence collapses because there's no room for differential, because the differential all goes this way. It goes to the left by 1 unit and goes up by at least 2. So there's no room for differential, and you can see the spectral sequence simply collapses. And even at S, and here we can also rate, say, the 2t minus S stand, 2t minus S equals 0 stand. You can also rate this is ZP directs on the class group. So which is like what K0 is, and this is what K1 is. So from here, it's pretty clear that it is pretty clear that the spectral sequences collapse because there's only at most, there's no room, simply no room for differentials. And the goal of my projects is to generalize the two theorems, the Quillen-Lichtenbaum and the Quillen-Borel theorems, to arting or to Dirichlet, or even more ambitiously, arting L functions. So let me now tell you what are those L functions. For simplicity, I only introduce Dirichlet L functions. So a Dirichlet character is the group homomorphism from the group of units in the mode n to the group of units in complex numbers. So this is just a working definition. If you read an actual number theory textbooks, they'll tell you like how to identify Dirichlet characters of different n. But here I'm just take this as my definition, a working definition. The Dirichlet L function attached to chi is this formal summation, where basically it's like in the Riemann zeta function, we replace the numerator by the values of the character. And I should also mention this chi of n, lowercase n is 0 when lowercase n and this capital N are not coprime. Otherwise, we just evaluate chi as a residual class of n mod n, mod capital N. So it's sort of a twisted version of Riemann zeta function. And again, first question, what are its analytic properties? So when chi is non-trivial, this function converges, has slightly better convergence than the actual Riemann zeta function, namely it converges in the right half plane, and it admits analytic conjugation to the entire complex plane. So there's no pole whatsoever. And also, just like the Riemann zeta function or Dirichlet zeta function, it admits an Euler product formula, where again, in each of the Euler factor, we add a chi of p in each of the Euler factor. And in this case, special values at negative integers, sorry, this is a typo. This is a typo. This should be L of 1 minus n comma chi, not this. At negative integers, the values of Dirichlet L function is no necessarily a rational number. Rather, it is in the extension of rationals by the images of chi. So it is going to be an algebraic number. It is an algebraic number. And also, half of times is actually going to be 0. So it has simple zeros at S equals 1 minus n when the parities of n and chi do not match. There's also a functional equation Again, we have to add some extra Euler factor to make this mirror symmetry work, but it's not exactly mirror symmetry in this case because we also need to invert the character as well to make this functional equation work. And notice this sigma cross is a Galois group of the n-cyclotomic extension of the rational numbers. So Dirichlet characters are basically abelian Galois representations. And Dirichlet L functions are indeed special cases of RTL functions attached to Galois representations of number fields, whereas F, K, L are all number fields. So, and I'm not gonna tell you the precise definition of RTL functions. It's too complicated and it won't help. Well, so it won't help. It will not be used in the rest of the talk. But I want to mention the RTL functions. They were defined in its most generality. It is defined using in the form of an Euler product, and I don't think there's a form to write it as infinite sum. So the goal of this project is to formulate the Quillen-Borel theorem and the Quillen-Lichtenbaum conjecture for Dirichlet homogeneity RTL functions. And what's the slogan? So the slogan is for an RTL function attached to a Galois representation, we want to say its order of vanishing and special values at this point are computed by, of course, I guess we want to say G equivalent algebraic K groups of OF, but where's the representation? In RTL function, the rho is a very important input. So the slogan is they're computed by equivalent algebraic K groups with coefficients in the representation. What on earth does that mean? So let's recall, non-equivalently, homotopy groups of a spectrum with coefficients in a abelian group is defined to be the homotopy groups X, tensor, or smash with the Moore spectrum attached to it. I guess people are more familiar with, say, homology groups with coefficients in a abelian group. There's a parallel notion of homotopy groups with coefficients in an abelian group, and in this case, we tensor the spectrum by this Moore spectrum. And just like the homotopy, homology groups with coefficients, there's also a universal coefficient theorem. There's also a universal coefficient theorem for homotopy groups with coefficients. Okay, so that's what we're gonna do. We'll make sense of this slogan. What the G equivalent homotopy algebraic K groups with coefficients in representation. So that's the end of the first part of my talk. Any questions? Any questions? If not, let's proceed. So I guess we all know as homotopy theorists, rational homotopy theory is supposed to be easier than integral ones. The same, especially in the equivariant setting. So let's first deal with that situation. So let's first state the equivariant and equivariant Quillen-Borel theorem. So by constructing equivariant Borel regulators, those Rn's in the Quillen-Lichtenbaum conjecture, Benedict Gross proved the following: let F be a number field with Galois group G. Then first, a K naught of OF, the rational part, of course, has trivial G action. And now we write MF for the set of complex embeddings of F. And this set has two actions, one by C2 on the right by the complex conjugation, and another by G on the left. Sorry, I probably switch. C2 is a left action by complex conjugation, and G is the right action by just precomposing with the Galois action. And then we define this set. Okay, so this is a free rational vector space generated by the embeddings, and we take we sort of basically, and then this space will have a C2 action by complex conjugation, and we take the -1 to the n eigenspace. And what Gross proved is the following. Then we have an isomorphism of rational G representations. So if you base change the algebraic K groups of OF in all degrees and tensor with Q, remember this is a rational vector space and it has a G action, and the G action is given by the following. So except for degree n equals 1, it's basically this is basically some eigens -1 to the n one eigenspace of this free rational vector space generated by embeddings. And at n equals 1, you have to take some hyperplane. You have to take a hyperplane. And if you still remember the formulas, which this corresponds to the fact that in, say, the Dirichlet unit theorem, there's an R1 plus R2 minus 1. This taking kernel corresponds to the minus 1. So what I prove is following. Basically what I prove is I lifted the construction by gross to the spectral level. So the same setup. And let KR be the connective cover of Artia's C2 equivariant real K-series spectrum. So here we'll have a C2 action by complex conjugation. And sorry for the notation. I know some of you might want to write K mass BBR, but you'll see in a moment that's probably worse than what my notation is at this point. So I apologize for that. So first, we can leave the regulator to spectral level as following. So first, we consider, first there's a map from K of OF into this mapping spectrum. So let me explain to you what this lambda does. So for each embeddings from OF into C, we have a map from K of OF into K of C, and you just assemble them together. And that will land in this mapping spectrum without, and you can check it actually factors through the C2 fixed points. So this is basically, you consider all embeddings of OF into C, you apply algebraic K-series factor, assemble all the embeddings together, and that's what lambda does. And you have to check, of course, it factors through the C2 fixed point. And the second step is, well, we just apply some sort of universal regulator. So there's a universal regulator from K algebraic K-series of C as a discrete ring to suspension KR, which is the Engelberg-MacLane space spectrum of R, and you can see that's why I didn't use mass BBR here, because it's gonna be very confusing if I use mass BBR at this point. And the claim is this the induced map of whose induced map on pi minus 1 is a regulator. It's what the regulator is. And furthermore, so we have this map, so you may ask, well, what are the fibers and cofibers? So the fiber, the cofiber of this map, of course, we want to base change to HR, is 2 copies of the Engelberg-MacLane spectrum for R. And this basically tells you the sort of a real or equivalently rational equivariant homotopy, naive equivariant homotopy type of algebraic K-series spectrum of OF. So basically, you have this part, which is fairly easy to understand, and then the difference is just 2 copies, basically 2 copies of HR, suspension HR. And from there, Benedict Gross stated an algebraic version of Quillen-Borel theorem for RTL functions. So consider an RTL function attached to a Galois representation for rho and denote the L vector space by rho underline. I'm distinguishing between the map and the representation. The statement is the order of vanition of RTL function at negative integer is equal to sort of the rho inverse eigenspace of the algebraic K group of OF. So you first twist it by rho, and you take G fixed point. That's sort of rho inverse eigenspace. And here you have to be careful. You have to take L dimension as an L vector space. And from there, it's not too hard to show the following. So basically, we can replace this rho inverse eigenspace by a G equivariant homotopy group. So basically, we twist the algebraic K-series space or spectrum by the equivariant spectrum attached to the representation rho. And you can see the right-hand side, this is precisely what I meant by equivariant algebraic K-series with coefficients in rho. So let me explain to you more about this equivariant Moore spectrum, which is going to be very important. So first, the Moore spectrum attached to a abelian group is a unique connective spectrum, such that its homology group is concentrated in degree 0, then which is an A. And the caution is this construction from A to M of A is not functorial. But nevertheless, rationally it is functorial, because rationally, Moore spectrum or Moore spaces are Engelberg-MacLane spaces. Which follows from Serre's theorem. So rationally, this construction, it is functorial, and that's why we can always lift an action, a G action on a rational vector space to a G action on the rational Moore spectrum. That's always possible. And then we just denote M rho underline to be the G-Moore spectrum attached to this representation. And then the proof of the Quillen-Borel theorem for RTL functions, it's just a few steps. So this is the result by Gross. And then we can use an equivariant universal coefficient theorem to move the rho. This twisting by rho is basically changed by this representation rho inside. So instead we tensor the algebraic K-series sequence by the Moore spectrum. And finally, so here it is still the G fixed points of the dimension of the G fixed points of this homotopy group. And finally, we can move the G fixed points of vector spaces to homotopy groups of G fixed points. And those two steps, they are differed by a homotopy spectral sequence, homotopy fixed point spectral sequence, which collapses in rationally because G is a finite group. So basically, once you have the Borel, you have the right setup and you have Gross's theorem, then it's just a few steps to deduce this homotopy theoretic equivariant homotopy theoretic version of the Quillen-Borel theorem for RTL functions. So previously, when I first had this result, I joked probably this is just, I should be able to finish writing this as a 1-page or 2-page paper. But turns out my preprint for this was like 10 pages long because there are other details that I need to cover. But yeah, I mean, rationally things are pretty clean. So before we move on to the integral part, the more scarier part, any questions before we move on?
Yeah, Ningchuan, you wrote down this, goes from the K theory of the complex numbers to, I think, KR smashed with like a suspension of the Eilenberg spectrum.
Yes.
What is that map? E is that?
Oh, okay.
How do you write that down?
So this map can be written down. So first of all, any map from K of C to this is equivalent to a real homology class, some equivariant homology or equivariant cohomology class of K of C, which are the universal regulators. So it's basically because rationally, suspension KR is basically, a wedge sum of equivariant Eilenberg spectra. So yeah, so here, this is not so easy to describe. It is sort of related to logarithm. In pi 1, it is, or pi naught, in this case, it's probably the logarithm. And the next one is sort of, I heard it's dilogarithm. So it's sort of some universal regulator that I don't have a good description for.
But the point is you just choose some cohomology classes. And
yes, just choose a cohomology class, yes. Okay, let's move on. So let me make a statement, make a conjecture. Let chi be a Dirichlet character and suppose the parities match. Then the following is hold up to powers of certain bad price. Of course, 2 is a permanent member of bad price in any situation. So what we do? So remember previously I told you the special values of Dirichlet L functions and negative integer is an algebraic number. So I can normally down back to a rational number. And my claim is this is equal to, probably I miss a plus minus sign. There's always going to be a plus minus sign. The sizes of those algebraic K groups, which look pretty monstrously complicated. So what are they? Let's decipher them. So this part, this is the integral, the more cross equilibrium spectrum attached to some integral character. So remember, this character, this is complex valued, but it uniquely factorizes through some cyclotomic extension of integers, where I require the first map to be surjective. And then this OCHI is basically the integral part of the Dirichlet character. And then now I twist the cyclotomic extent, the algebraic case or cyclotomic extension of integers by this equivariant Moore spectrum. I take the fixed points and take homotopy groups. So this is basically what I meant by equivariant algebraic case theory of the zeta n with coefficients in chi or OCHI. But the first question, does this MOK even exist? Because I mentioned to you, this Moore spectral construction is not functorial. So there's no guarantee we can lift the character from abelian groups to spectra. And that's actually Stinor's question. So Stinor's question is the following. Let it be a abelian group with a G action. Is there a G action on the Moore spectrum of A such that the induced action on the zeroth homology group is isomorphic to the prescribed action? The answer is no in general. So Gunnar-Carlson has constructed counterexamples for every group of the form CP times CP. So basically, every time you have a non-cyclic abelian group, there's always going to be a counterexample. However, in my thesis, I prove for any abelian character of a finite group, there's always an integral equivariant Moore spectrum. And it exists as a G-stable complex. But even this is the case, there's still no uniqueness. There's still no uniqueness in this construction. So there are many different constructions. So now let me explain to you how this construction works. So the idea is first, again, we have this factorization. So it suffices to construct, so where this per se n sends a generator of Cn, cyclic group of order n, to a primitive root of unity. And then you can check that this per se n is an external tensor product of its prime factors. And now, so it suffices to construct a lift for each of those cyclotomic representations. And then this is from what Charles Resk told me, which is very, very important in this whole story. So basically, what you notice that there's a Schrödinger sequence of CPV representations. So here we get this by saying, what is this? This is ZT modulo the cyclotomic, the cyclotomic polynomial of degree p minus v of p to the v, and you notice that cyclotomic polynomial is precisely, and from there you can write down this Schrödinger sequence. And from there, we just define the equivariant Moore spectrum by taking the D-suspension of the cofiber, because this free algebra or the G module corresponds to basically the G itself, and this is basically the G module generated by this orbit. So we just take the orbit and we take the sort of the fiber or D-suspension of the cofiber, and now we just set the equivariant Moore spectrum for this per se n to be the external tensor product of all those equivariant Moore spectrum for these prime factors, and then for OK, for some reason I have to do some dual and then pull back, but that's some technicality. You don't need to do this. And here are some pictures. So when here are some pictures. Well, let's just suspend everything. So there are pictures. So let's do 5 cases simultaneously. We have a base point, and then the zero equivariant cell is CPV mod CP. So let me explain to you notation. This subscript means the congruence class modulo this number. So here this is 0 mod 2, 1 mod 2, 1 mod 4, 0 mod 4. And the group basically acts by, say you have some element A in say n, then it just changes this label and say 0 to n mod 4. And then how do you add one cell? The one cell is precisely CP itself, and it is glued to the 0 cell. One side gets glued to the base point, another side gets glued to the residue class. So you can say here, in this case, 1 is congruent to 1 mod 2, so it's glued to here. 3 also congruent to 1 mod 2. And when it acts, say 4 acts on this spectrum, basically it just sends 1, the generator sends 1 to 2, 2 to 3, 3 to 0. And then the generator flips 0 and 1. So you should stare at this picture and then try to visualize how the group acts on those finite complexes. And the most important thing is the group, when it acts on those spectra, the induced map on the first homology group is precisely the one associated to the cyclotomic characters. This is basically I draw this picture from this formula. It's like here, this is a 0 cell. This is your 0 cell. 0 equivariant 1, 0 equivariant 0 cell. This is your equivariant 1 cell. And that's how I draw these pictures. Okay, so that's the equivariant Moore spectrum. And from there, once we have this, we can still remember one important step in connecting the L functions with algebraic case theory is the Thomason spectral sequence. So as a first, so let me just say, so a natural way to try to generalize the classical Quillen-Lichtenbaum to Dirichlet L functions to mimic the diagram. And there is an Iwasawa main conjecture for Dirichlet L functions as well. So you may wonder, is there a Thomason spectral sequence also? Can we also incorporate Thomason spectral sequence also incorporate the Galois representations in Thomason spectral sequence? So there are two. So to do that, actually, there are two observations. One is the category of Galois representations can be identified is equivalent to the category of locally constant shapes on etal sides. Second, as I mentioned, there's a Iwasawa theory for the Dirichlet L functions, where in the system, in here, we have to trace the coefficient by the locally constant shape corresponding to the character. So you may ask, is there a chi-twisted version of a Thomason spectral sequence? The answer is yes. Actually, we can propose things more generally. So if you have a finite tau cover of schemes and you have a G representation, then suppose A is flat over ZP and then the Moore spectrum exists, then we have a Thomason type spectral sequence. So here we just in the E2 page, the coefficient is no longer ZP, but rather it's something related to twisted by the character. And on the K1 open algebraic K series side, we twist the spectra by the equivariant Moore spectra associated to row. So if we want to persuade this way, then the next step will be how can we do this in the Nielsen image side? Because that's where algebraic K theory actually lives, and that's more complicated, and we're still working on that. Here's another approach. Another approach is to just bootstrap from the classical Quillen-Lichtenbaum, because there's some relation between between Dirichlet and Dirichlet, Dirichlet zeta function and Dirichlet zeta and Dirichlet L as follows. Let F be an abelian extension. Then by the Kronecker-Weber, it is containing some cyclotomic extension. Then the Dirichlet zeta function factors as a product of Dirichlet L function is a pretty crazy factorization. It ranges over all characters whose kernel containing this Galois group. And actually, it can be simplified if we accept those Dirichlet L functions are also Artin L functions. So just do the multiplication over all characters for this Galois group. And in particular, in the simplest non-trivial case, when F is a Gaussian is a QI, then basically that's n equals 4. Let sigma be the sign character, then we have this formula. Basically, the Dirichlet zeta function for QI is equal to the Riemann zeta times this Dirichlet L. So we have this fairly simple formula, factorization formula. And we know this zeta QI is related to algebraic K theory of the Gaussian integer. And the zeta Q is related to algebraic K theory of Z. So you may want to say, can we say something about this factor? Can we relate those two spectra? Of course, there's a natural map because there's an inclusion from Z to Zi, which induces a map on algebraic K series spectrum. And of course, we can just take the cofiber. And the claim is the cofiber is precisely some sort of twisted algebraic K series spectrum by that equivariant Moore spectrum. Because here, this is the representation sphere S1 minus sigma, which is also a model for the equivariant Moore spectra attached to the sign character. And let me explain to you why this should be true. And also another thing is F induces an injection in homotopy groups when 2 is inverted. And from there, you can say from this cofiber sequence, we get a line exact sequence in algebraic K series spectra, algebraic K groups. And once we invert 2, those long exact sequences split up into shorter ones. This corresponds to zeta QI. This corresponds to zeta Q. So their ratio will be precisely the size, the special value of this Dirichlet L function. And it is therefore we have basically proved the Quillen-Lichtenbaum, at least for the simplest non-trivial Dirichlet L function, up to powers of 2. because I mean the original Quillen-Lichtenbaum also says everything up to power 2, so we didn't do anything worse than the original version. And maybe let me explain to you a little bit more of the proposition of why this is true. So this uses the G equivariant complex structure of the equilibrium spectrum, namely this S sigma minus 1 sits in this C2 equilibrium cofiber sequence. And we just map everything into the algebraic K-series spectrum for the Gaussian integer and then taking C2 fixed points. And also, let me also explain to you why that map F induces an injection in homotopy groups when 2 is inverted. This is because the inclusion, even though it's not a tau, it's symptomic. And from there, there's a transfer map. So the composition is multiplication by 2. So that's why once 2 is inverted, F becomes the injection. And the 2 important ingredients in this proof is we know that this first, that algebraic K-series spectrum of the I is a C2 spectral mapping factor. We use this in an essential way. And also we can construct C2 cross from those Moore spectrums. This is a trivial character, this is a sign character. And now we are working on to adapt this proof to more general Dirichlet functions. And the current status is we have proved that the statement holds, the conjecture holds when the image of chi, the size of the image of chi is a prime power. The reason is in that case, equilibrium spectra is just a has two equilibrium cells, so everything is easy. So the same argument would apply, but more generally, we need to compute this pretty complicated Borel-Dunkel homology. So this is Cn, where this is CM extension, and this is at the equilibrium spectrum, and this is basically you take the equivariant algebraic K groups of OF as a Mackey functor. We have to compute something like this, and then there's equivariant anti-Hertzsprung spectral sequence. So it's very complicated, and that's what we are working on now. And that's everything I want to say. Thanks for your time and attention.
Questions? Yes.
So in your construction, so when you construct these Moore spectra and have problems with them, you're always going to be smashing them with some kind of algebraic K-theory spectrum. Do the problems with existence and uniqueness still exist in like the category of KOF modules, or are they?
I believe so. I believe so. So I think in one, so it's, yeah. So like in this case, we could have chosen, instead of S1 minus sigma, we could have chosen S sigma minus 1. And then the whole sequence will be, whole sequence will be flipped. And I believe in those two cases, the answers we get will be different. And it's sort of like the difference will be something similar to the exotic element in K1 Oko Picard group. It's like for different models of Moore spectra, like this E2 page of the the twisted Thomason spectral sequence will be the same, because after all here the input is just the representation itself. There's nothing spectral here. So you have two things that has the same E2 page. You have the two spectral sequences with the same E2 page, but there's no guarantee that their higher differentials are the same. So you get something similar to the phenomenon of the exotic elements in K1 Oko or K1 Oko Picard groups.
Other questions?
You mentioned that you'd like to be able to take this theorem that you have with Eldon right here on the screen and get rid of the K1 and then probably replace Ital with like Moat or some decoration like that. Mm-hmm. Is that also a work in progress, or what's the status of that?
I think Eldon has some idea, but we haven't been able to verify everything yet.
Yeah, that seems hard.
Yeah. Yeah.
Great.
Yeah, can I guess just very quickly? So, am I understanding right that the method, in some sense, is using this spectral sequence and the pre-existing proof of Quillen-Lichtenbaum for trivial coefficients, or are you actually like going into the guts of Wojewodsky-Rost's proof and reproving it?
Yeah, that's a great question. Thanks, Craig. So, sorry, I wasn't being very clear here. So it's actually a sort of it's two parallel strategies. So one strategy is just to mimic the original proof of Quillen-Lichtenbaum. So first, Iwasawa theory from PIDL function to Itaku homology group, Tiaku homology group to K1 algebraic K series spectrum, and comparison with the integral version. That's one strategy. And another approach is a different strategy. It's independent of the previous strategy. Like the last few slides are independent of the twisted Thomason spectral sequence methods.
Okay.
Yeah, sorry about this.
Sean, I have another question
Sure.
about the Thomason spectral sequence again. So, yeah, so what do you get if you let's say you assume, I don't know, you've got something smooth, so you can have some kind of motivic filtration on K theory. What do you get when you look at the sort of G action on the motivic filtration smashed with this equivariant Moore spectrum? Like, is that something that is close to what you might expect to need in order to get the spectral sequence, or is that maybe really far away from what you want? Because at least the spectral sequence from motivic cohomology to algebraic K theory, at least if I remember correctly, is some kind of slice spectral sequence in the motivic homotopy category. And so I'm sort of curious if there's some existent technique which could get you close to that, but maybe, I don't know if that's the right thing.
I think that's something definitely related. So what we want is a similar spectral sequence in the motivic setting, but for that, several things needs to be smoothed out. Like, what is rho? Rho is an Itaú shift. It's not clear how to do it Nisnevich, like in the Nisnevich side. That's the first thing. And I guess on this side, you can of course write down what you want. Like algebraic K series spectrum, of course, it has a G action. If X has a G action, since we are doing in this setting, and of course you can twist it with more spectrum, taking genuine G fixed point, everything's fine. So yeah, but I don't know. And also once we have that twisted, equivariant twisted motivic spectral sequence, the next question is how about comparison? How to compare the two things, and in what range we have a similar Blavatsky-Rost comparison theorem, like the ISO in certain range. And also, as you can imagine, this spectral sequence most likely do not collapse unless you invert the order of G. So that's another complication.
Okay.
Can I ask about that proposed comparison? I mean, so in the non-equivariant setting, it's just like you expect it to agree in sufficiently large degrees. What does sufficiently large mean? Is it just in terms of equivariant homotopy groups, or should you be grading over the Picard group, over the representation spheres?
That's a great question, and I would like to say we have no idea.
Okay.
We have no idea at this point. We have no idea at this point.
Yeah, cool.
Makes the question the best.
Yeah, this equivariant computation, I don't know, maybe it's something, I don't know, maybe at the end of the day we'll get eventually reduced to the same computation. Maybe we'll eventually reduce to the same computation. Because after all, this group is a motivic homology group. So maybe the two methods will converge. And this is indeed what we need to compute even from the other approach. That's also possible.
Other questions? Well, we had a wonderful discussion, and thank you so much, Ningchuan, for the very interesting talk. Let's thank Ningchuan again for I think that we are done. I don't know how much interest people have in going to beers, topology beers today. It's an unusual thing. And I can join you for just one beer, perhaps. Is there any interest in going to beers?
I feel like yours better.
Yeah.
Yeah, so okay, no beers today, even though everybody have seen this in the ad sent by Calista. It's an unusual week, so everybody please have a great Thanksgiving, and
Yeah.
we'll rejoin in a week. And thank you so much again, Ningchuan, for
Yeah.
for a very interesting talk.
Yeah, my pleasure.
Thank
Happy
you,
Thanksgiving.
Thank
everyone.
you. You too.
Bye, everyone.
Bye-bye.
Thanks again for the talk.
See ya.
Yeah.
See you. So I don't know if